Today we will discuss about magnetic flux density. In electrostatics, we have studied that the electric flux was proportional to the number of electric field lines. Similarly, and the flux density was proportional to the number of electric field lines per unit area. So we can say number of electric field lines per unit area. So that we have studied in electrostatics. Similarly, in magnetostatics, the magnetic flux is proportional to the number of magnetic field lines and the density that is represented by B, magnetic flux density, is proportional to the number of magnetic field lines divided by unit area. Number of magnetic field lines for unit area. So similar to the electrostatics, we have same relationship for magnetic flux and magnetic flux density. So from here we have the unit of magnetic flux density as magnetic flux per unit area, that is Weber per meter square. Let us consider a magnet, and we know that there will be north and south pole, and magnetic flux lines are originating from north and terminating at south, and they are forming the closed path. Okay, like this. And if at any cross section, at any part of this, the lines are passing like this here, and inside similar number of lines are passing from south to north. For any closed surface, the number of lines at any surface that are incoming and outgoing are same. So for any surface, the total flux enclosed by it will be 0. In case of magnet, or we can say in case of magnetostatic, the flux by any closed surface will be equal to 0. And we know the flux can be written as B dot ds for any closed surface. According to the Gauss law that we have studied, it will be equal to 0. And if it is equal to 0, then this in volume integral form can be written as that is divergence theorem, if we recall. Then del dot B dV for volume integral, it will be equal to 0. So from here we can say this will be equal to 0, because for it is valid for every volume. So from there we can say this will be equal to 0. So del dot B will be equal to 0. Related from electrostatics. Similar to that, it is the Gauss law of magnetostatics. Okay, so we can say this is Gauss law of magnetostatics. Okay, and this is also known as divergence of magnetic flux is equal to 0. And if we recall, in case of electrostatics, the divergence of D was equal to the rho v. This is differential form of Gauss law, and this is integral form of Gauss law of magnetostatics. Okay, so from here we have del dot magnetic flux density is equal to 0. This is possible only when the number of the flux in and flux out are equal from any closed surface, and that is possible only when the pole pairs exist. It is not possible in electrostatics. However, in magnetostatics this is possible. So here we can say due to the this we can say the monopole does not exist in a magnet. So we can say no magnet monopole exists. The magnetic flux density B is similar to electric flux density D, and we know D is equal to epsilon naught E in electrostatics. In free space we are talking about, then the electric flux density was equal to the epsilon naught E. Similarly, in case of magnetic flux density, B can be written as mu naught the magnetic field intensity. Epsilon naught is known as permittivity, and this is causes the opposition to the electric field lines passing through the surface, or we can say from material. So in this way it causes the resistance to the magnetic field lines. However, this is permeability. It allows the magnetic field lines to pass through the surface. So this is the resistance, this is allowance. So it resists the magnetic field lines, it allows the magnetic field lines. Okay, so from this is known as permeability and permittivity. The value of mu naught is 4 pi into 10 to power minus 7, that is for free space, and for any medium it is written as mu r mu naught, whereas it is written as mu. This is the relative permittivity with relative to the free space, where mu r is always greater than 1 other than the free space. From here we can find that the unit of B is Weber per meter square, whereas from here we find B depends on the medium, whereas H is independent of the medium. Okay, so these are few points regarding the magnetic flux density and the terms related to that. Now we will try to find the magnetic flux density in case of coaxial cables. So let us try to find the magnetic flux density due to coaxial cable. Okay, there is a cable of outer radius B, inner radius A, this is A and this is B, and the current that is flowing is I. Okay, now if we choose an Amperian path for rho lies between A and B, and we choose an Amperian path for that, then we can say that H dot dl will be equal to the I enclosed from Ampere's law. We know this, we already have studied. So from here we can have H dl. In case of this can be written as, for example, we are talking about this length, then we can say rho d phi. So dl can be written as rho d phi. H will be in the direction of phi, so the dot product will give you 1. It will be I enclosed if we get the integral of this for closed path. And here we can write H rho, the full path gives 2 pi, that will be I enclosed, and from here we have H is equal to I enclosed by 2 pi rho. And if we multiply from mu naught, or we can say if it is free medium, then if we multiply from mu naught, then we can get B. So from here we can write B is equal to mu naught I divided by 2 pi rho. This will be in the direction of the phi direction, A phi. From the Gauss law, the flux can be find out B dot ds for the closed surface, and the number of lines that is passing from here will be B we have from here, that is mu naught I 2 pi rho in the direction of A phi dot ds. ds, consider a portion like this and the lines that are passing from there. So if we are considering a portion like this, that is inside the towards the center, slice towards the center, and for that purpose the ds can be written as the rho d rho times dl. So that will be d rho and dl, length of the conductor. So from here it will be surface integral. Okay, and the area of that vector will be in the direction of the curling of the finger, that will be in the direction of a phi. So this a phi will give you the same direction, mu naught I divided by 2 pi rho d rho and dl, where rho is varying from A to B and rho is varying we can say from 0 to full length. Consider it 0 full length. So mu naught I divided by 2 pi d rho by rho, we can say log rho, where rho is varying from A to B and dl will be total length. From after the simplification we can have 2 pi natural log B minus log A, so it will be B by A with length of the conductor. So this is the total flux from the path which includes the current I. Okay. Now let us discuss magnetic forces. We know that electric field applies forces on the charge, whereas the magnetic field applies force on current. It means that if there is a current in magnetic field, then it experiences a force. And if a charge is moving in magnetic field, it means if the charge is moving, then that will cause the flow of the current. So due to the current, it will experience a force in magnetic field. Okay, that is why moving charge experiences a force inside the magnetic field. Okay, so moving charge will experience electric as well as magnetic force, as electrostatic property is also applicable if charge is moving. So from there we can say if E, the electrostatic force, is nothing just QE. We have studied this. And the magnetostatic force, we can say this is U cross B. Okay. The Q is the charge, U is the velocity from which it is moving, B is the magnetic field in which the charge is moving. And if we wish to find the total force acting on the moving charge in the magnetic field, then due to the electrostatic force, it will be QE, and due to the movement, the force, that will be QU cross B. The combination of these two will be experienced when the charge is moving in magnetic field. So this is nothing but Lorentz force. It is known as Lorentz force. Okay, from here, this is the total force experienced by a charge Q when it is moving in magnetic field B with a velocity U. Okay, So based on it, if a current carrying conductor, that is flowing the current I through that, is placed in a magnetic field B, magnetic field density, magnetic flux density or magnetic field, consider the same for explanation. So the current carrying conductor is placed in magnetic field, then it will experiences a force. Let us try to find how much force it will experience. So for that purpose, consider a part of this conductor. So the total charge that will be there, we can say IDL, that will be current element. This will be dq over dt, that is I, and dl for this portion, dl current element. From here we can say dq times dl over dt. It is nothing, the movement of the charge, rate of flow of the charge. So we can say dq, this is the velocity of the charge. Okay, so IDL can be written as this. So if we talk about the force at this portion, then we can say the FB, that will be equal to this IDL, or we can say dq. The formula we have U cross B, we have this formula. The magnetic force that will be experienced at this portion, the charge of this portion is dq, and due to that it will experience a force like that, and this can be written as IDL cross B, you can write as well. So from here, if we wish to find the magnetic force at this portion, then this is given. If we wish to find for full length of the conductor which is in the magnetic field, then we will integrate this, and similarly we have to integrate here as well, IDL cross B, and the integration should be for full length. Okay, now if the current density is I, then we can write I, line current is there, then the charge will be IDL, and if it is surface current, then it will be JS DS cross B. Okay, for surface the FB can be written like that, and it can be taken out, JS cross B can be in, so we can write in this way as well. And if it volume current is there, then we will write JV dV cross B for volume integral. So in all the cases, either it is line current, surface current or volume current, in all the cases we can find the force experienced on the conductor which is carrying the current if it is placed in magnetic field B, that is given here. The condition is that B is uniform. Okay, and now next question arises, how this magnetic field generated. So we know that the flow of the current causes the magnetic field, so we can assume another current is there, that is the current is flowing through that, and that current causes the magnetic field, and that field due to that field a force will be exerted on the first conductor. So in this way, if we can say there should be two current carrying conductor nearby each other, and one will generate the magnetic field and other will experience force due to that field. So the conductors will apply force on each other. Okay, and considering this, let us assume first conductor is there, it is carrying current I1 and the length of this is L1. Consider another current of I2, it is having length L2. Now assume that this I2 is generating the magnetic field and this current carrying conductor is in that magnetic field, so force will be exerted on this due to this magnetic field. And similar condition can be considered as well for this conductor, that is the field will be generated from this and the current carrying conductor which is carrying current I2 is placed in this field and it will experience a force due to this field. So in both the way we can write, so the force that, consider the first case, the force that will be experienced at dl from this current carrying conductor which is generating the magnetic field will be d from this small portion, say df. Okay, so if we are trying to find the force on one, so we can say force on one. For this small portion we can write df, and if we are getting the force for this small portion, then we will write d. So according to that we can say the force experienced at this small element will be I1 dl1, okay, cross the field that is generated by this here, that is db2, okay, idl cross b that we have here. So this is the current element and this is the field from here, and the field, if this length is r12 and db2, we can say the field due to this element at this point means for I1 dl, we can say db2 can be written as mu naught I2 dl2, this current element, divided by 4 pi the distance between these 2 points square, this with the unit vector in this direction r12. This is the field at this point due to this current element I2 dl. Okay, now put it here, we will find df1 will be equal to the I1 dl1 cross mu naught I2 dl2 divided by 4 pi r12 square cross ar12. Okay, and if we will simplify this, then we can say mu naught I1 I2 divided by 4 pi r12 square dl1 cross dl2 cross AR12. Okay, this is the force at 1 due to this current element I2 dl2. If we wish to find the total force acting on this current carrying conductor from this current carrying conductor, then we should integrate this for full length of L1 and L2. So in final form, we can say force on this will be F1 for length L1, for length L2. If we integrate for full length, then it will be I1 I2 divided by 4 pi R12 square, and dl1 cross dl2 cross AR12, this will be there. Okay, so this is the total force at this line from this line, when this line is carrying conductor I1 and I2. Similarly, same force will be exerted at this with opposite in opposite direction.